Hey, so this video we're going to be looking at a velocity selector, and then we're going to be going on to a mass spectrometer as well. If you're just looking for the mass spectrometer part of this, which is I'm going to be doing second, I'll put the time which it starts on the video on the screen just there now. So you can just skip to that bit if you want to see the mass spectrometer, but know that part of the mass spectrometer relies on this bit of the velocity selector, so it's definitely worth watching both. Right, so we're going to start with, we've got an exam type question here, and we're going to have different parts of this which we have to discuss. So I'm going to sort of pose possible exam style questions as we go through, and we're going to go through and answer them. So a general part to this, the first stage for this will be, what speed would the particle be going at after it leaves the acceleration phase here, given that we know the charges on these two plates and we know the charge of the particle and perhaps at this point the mass of the particle here. Sort of derive an equation for the velocity at which it leaves this stage of our problem. So for this, what we're going to do is we're going to use a conservation of energy, and we're going to say the kinetic energy, so the sort of the velocity it's going to be leaving there, is going to be equal to the potential energy caused by its charge and the charges on the plates here and here. So we can use our KE equals PE, and we have our Q, and this is delta V, and this V here is velocity. So now we're just going to solve this for velocity. So this is very simple. We'll multiply both sides by 2, so you have 2 Q delta V equals M VA squared. Divide both sides by M, so we can get rid of our M there, put all of this over M, and then we're just going to take the square root of both sides to give us VA equals the root 2Q delta V over M. Nice and easy. So that's an equation for our velocity at leaving this. And I would say, okay, so what are the charges on the two plates which we have here and here? So we're dealing with a negative charge, as we can see. So we're going to want it to be attracted to this plate, so it pulls it forward, and repulsed by this plate, so very easily negative and positive. So that's bit's nice and easy. Now we're going to come on to this stage. So we're wanting this to go straight up and through here. Now we have a B field, which is our magnetic field, and this is going into the page. And we have an electric field, which, as we know, always flows from positive to negative. You may also be asked, which way does the electric field flow? Draw the lines on, so you always do positive to negative. You may be asked, if a particle is going straight forward and you have the field drawn on, or just the charges on either side, does the magnetic field go into the page or out of the page? You can try whatever hand rules you know, where you might use current as your first finger, your field as the second, your force as the other. You could do it whichever way you've learnt to do your sort of hand rules, shall we say. And you can use them to sort of say which way the field goes. Anyway, so we have a negative charge here. So our negative charge is going to be pulled up towards a positive plate, going in this direction, and our magnetic field is going to force the particle to go towards the negative plate. So for this to be completely a straight line and going through the slit at the end, both forces need to be equal. Now I've got a bit more of a crude drawing of this here just to draw on, so because this will be a bit complicated with all the markings on it. And what we're going to find is we've got the force due to the electric field acting that way, and we have the force due to the magnetic field acting that way. And for this to achieve a completely straight line going all the way up means that FE must equal FB. And now FE, we'll just write out what these are. That's just the charge by the electric field, and the force due to the magnetic field is the charge by the magnetic field, but also by the velocity. So this is where the actual speed of the particle alters the path it's going to take. So if we just equate these two, we have QE equals q b v. I'm just going to put v instead of va each time, but no, it's a velocity, not any voltage. We can get rid of the q's on each side. Then we can just, I will put the a there, and then you can just rearrange for our velocity, which is va equals e over v. So that's an equation there for the velocity which we'll get through. So when e over b is equal to the velocity of whatever we'll get through. So if you want to alter what velocity goes through, if you want to select the velocity, then you just alter e and b respectively until you select whichever velocity you'd like to go through. So that's that bit. And you can see then that if it's depending on the path you take, you might be given something like this. So two alternate paths going across, and our particles being here and here. Obviously our one going through, and it would ask you which one was too slow, which one was too fast. So this relies on velocity. So if it was really fast, then the magnetic force is going to win out. So this side here is going to be too fast, and this side here is just going to be too slow. That's very, very simple to go through, really. Hope with me so far on all of that. So that's sort of how the typical velocity selector works. So now what we can do is we can move on. And we're going to go ahead and we're going to take a look at the mass spectrometer. Now what I've done is I've taken this whole section here and shrank it down so it's sort of a less detailed bit there, but that's what it is. It's that there. And I've wrote some equations we're going to need. You probably wouldn't be given these in an exam, so you have to just memorise them, but it's really not hard. You should know this from mechanics sort of anyway. Right, so they're the two relationships we found earlier. And what we've got now, our particle is following this path, which we'll just pretend straight. You can see it's not quite straight, we'll pretend it is. And it's going through, and it's going into another B field, noted as B sub naught. And this field now is coming out of the page towards us. You could be asked to draw the field on for another exam question. Which way does the field go into the page? They may provide you with a field and say, because this is our detector here, where should your detector be? Now if this was crosses, so going into the page, our detector would have to be on this side, because as we know from here, our magnetic force was pulling us this way. But now it's coming out of the page, so it pulls us in the opposite direction. And you might be asked to explain sort of what's going on here, how does this work, all of that kind of thing. And I think a good way to do it is to derive yourself an equation first, and then do your written example of explaining what you're trying to say. So we can look here, and most of what we need is here. And as it goes through, it's going to arc around to the side and hit the detector. And wherever it hits the detector, it's going to know the radius of the arc. And from the radius of the arc and everything, you can, and if you have a known velocity, because only a known velocity is going through here because of E and B, and you know your B there, you can detect whatever mass is going through. This is a mass spectrometer. So this bit you probably wouldn't know your mass, you just accelerate something. Only a certain velocity is going to go through because of velocity. The mass doesn't matter when it gets through here, but then it's going to matter here. We'll show you as we go through. So you have our equation here. So you have our Q, VAB equals MVA squared over R. So first we're just going to get rid of our two V's on the other side, and we're going to write this down again. So our Q, B sub naught is now then going to equal M, VA over R. Notice we've lost the power and lost the V on that side. And we're solving for M, so we move the R over to the other side. R, Q, B sub naught equals, and we'll move the M down as well at the same time. No, sorry, we'll move the VA down at the same time. Equals M over VA. And then we're going to sub in our value for VA, where our VA equals E over B. So our B is going to then go to the top, because what we actually have then is R, Q, B naught over E over B. So our B goes back up to the top. So we have our M is equal to R, Q, B, B naught, all over E. And notice that we know everything here. We can get the radius, that can be calculated from wherever it hits on the mass spectrometer, on the detector, sorry, of the mass spectrometer. We know the charge of whatever we're putting in. We know we're controlling, in fact, all three of our fields here. And from this, that can then tell us what mass is going in. And you have this now, you'd write this down in the exam, you'd say, this is our equation for mass, and then you just explain that by controlling these three, you can alter what velocity is allowed to pass through this slit, saying about how if it's too fast or too slow, it's going to hit the other sides. And you can say that as it enters this field, it's going to arc round, giving a sort of a semicircle, it's going to hit a detector, and from wherever it hits the detector, you'll be able to determine R, and when you know R, you can then determine the mass of whatever's hit the detector. And that's how the mass spectrometer works. There's not really much math involved, so it's not too hard, but it's something you might want to get used to writing out because it's a very, very common question in electricity and magnetism papers, and so is the velocity selector section. So I'm just going to go through that one final time with both parts. With a velocity selector, we're accelerating something here. We're using the kinetic energy is equal to the potential energy, so we have the Q delta V is equal to half mv squared going through here. It enters the field. For our negative charge, it can be pulled towards a positive plate, and our magnetic field is going to pull it towards a negative plate. We alter these two to allow a certain velocity to go through. For this stage, we can control these two, and we know because of M is part of the half mv squared side, we know what mass is going to go through there, so that's how you can determine the mass here. And on this, we're just accelerating up to any speed, only allowing a certain velocity to get through, and then using whereabouts it hits the detector to determine the mass there. So that's the two parts of the problem. And if you want to see anything more from my channel, then just go ahead and click down here.